A heavy industrial turbine generates massive physical momentum as it spins. Despite being a single solid object, its constituent parts are moving through space at vastly different rates. Atoms on the absolute outer rim of the turbine may travel at hundreds of miles per hour. At the same time, atoms located near the exact center are barely moving at all. To maintain its structure, the object must satisfy the rigid body constraint, meaning it has a perfectly definite and unchanging shape, let the distances between all pairs of its particles remain fixed. This cross-section shows the speed difference. A particle on the outer edge traces a massive circumference, requiring high linear velocity to complete its rotation. A particle closer to the center traces a tiny circumference, requiring only a low velocity. Because linear velocity is specific to a single point, it cannot describe the motion of the object as a whole. We require a metric that is constant across the entire body. To find this constant, we shift our focus away from the physical distance traveled and toward the angle swept by the object. This is angular displacement, the angle a rotating body sweeps through over time. Regardless of distance from the center, every single point on this rigid body stays perfectly locked on this line, sweeping the exact same angle simultaneously. The ratio of this angular displacement to the time interval is defined as the average angular velocity. Unlike linear speed, angular velocity is a unifying value. It allows us to describe the rotation of millions of divergent particles with a single shared number. Average velocity only captures the overall motion over a very broad duration. To calculate a rotating object at a specific moment, we must refine our time interval. As the time interval approaches zero, the average values shrink toward a single point on the circle's path. This limit is the instantaneous angular velocity, d theta dt, denoted by the Greek letter omega. We link the body's rotation to its particle's speed. The linear speed, v, equals angular velocity multiplied by the perpendicular radius. Here, the radius acts as a geometric scaling factor, translating the shared spin into the specific speed of a single point. For a particle located exactly on the axis of rotation, the radius is zero, meaning its linear velocity is also zero. Conversely, a particle at the maximum distance from the axis achieves the highest linear speed. While the equation v equals omega r successfully calculates speed, it only provides a scalar magnitude. It cannot describe the three-dimensional direction a particle moves in space. To find that specific direction, we must move beyond two-dimensional circles and view the rotating body in three-dimensional space. Here, we must treat velocity as a vector, possessing speed and a precise directional trajectory. This requires us to also represent angular velocity as a three-dimensional vector. We face a challenge, assigning a single straight-line direction to a movement that is continuously curving. We resolve this by using the right-hand rule. When your fingers curl in the direction of rotation, your thumb points toward the fixed direction. Your extended thumb points directly along the axis, creating the angular velocity vector, omega. This single vertical vector now defines the exact orientation and plane of the entire object's spin. With this vertical vector established, we calculate the exact 3D trajectories of the body's internal particles. To perform this calculation, we must know exactly where a particle is located relative to the axis. We define this using a position vector, r, which points from an origin on the axis directly to the particle's coordinate. Note that this 3D position vector is different from the perpendicular distance to the axis. They form two sides of a right triangle. To find the velocity, we use the vector cross product. This operation combines two vectors to produce a third vector that is mathematically constrained by their geometry. The velocity vector, v, is equal to the angular velocity vector crossed with the position vector. By definition, the output of a cross product is always perfectly perpendicular to both of its input vectors. Because omega is vertical, the velocity vector must be perpendicular to it. This forces the particle's movement to stay within a perfectly flat horizontal plane. Simultaneously, the velocity must be perpendicular to the position vector, forcing the trajectory to point perfectly tangent to the circular path. These two geometric constraints automatically calculate the exact physical trajectory of the particle in three-dimensional space. The magnitude of this cross product is defined as omega r sine theta. Because r sine theta is geometrically equivalent to the perpendicular radius, the math automatically scales the particle's speed based on its distance from the axis. The cross product acts as a geometric engine, translating a fixed axis and a coordinate into a precise linear trajectory. In a high-precision mechanical gyroscope, every single internal particle follows these fundamental geometric laws with absolute and total consistency. We can now see how the divergent speeds we observed in the turbine are reconciled. The formula V equals omega cross r provides a unique solution for every coordinate in the body. For a particle near the core, the position vector is short, resulting in a low-speed tangent vector. For a particle on the outer rim, the longer position vector results in a much higher linear speed. Throughout these variations, the angular velocity vector omega remains the single constant that defines the rotation of the entire body. This alignment ensures every particle, from those in simple wheels and massive steel beams to those in planetary bodies, moves in coordination to maintain the solid geometry of the object.